In this lesson, we will introduce the idea of a series. So let's start by remembering a notation that we have used in the past, which this is what we refer to as a sigma notation. And what the sigma notation means is just we're going to be adding certain values or expressions up to a certain point. And recall that when we use a sigma notation, what we have in front of the sigma notation is what we're going to be evaluating, the expression that we're going to be evaluating, and the bottom side of a sigma notation, this is my starting point, and the upper part of the sigma notation, this is my ending point. So this is how we read sigma notation. We're going to be adding this expression, and we're going to be evaluating that expression up to the term of n. And that's exactly what has been said here. If I let I equals to 1, well, that's I1. Then I'm going to add the next one, which is when I is 2, which is I2, and so forward. But let's actually do two quick examples so we can review what the sigma notation means. So again, start by identifying what's the expression that we are evaluating. We're evaluating the expression of T3I. And notice that we're going to be starting when my I is equivalent to 1, and we're going to end when my I is equivalent to 5. So the way that we evaluate sigma notation is we take a look at the expression. Before we get anything done, we got to make sure that we're talking about the same variable, so they're both i's. So what's going to happen is I'm going to go to my expression and I'm going to substitute I be equivalent to 1. And notice that this is the expression that we do have in front of us, but now I is equivalent to 1. As a matter of fact, let me do different colors so you can see what's going on here. All we did, we got our expression and we substituted I to be equals to 1. And that's it. This is my first expression evaluated at 1. Since we're using sigma notation, we have to add the next evaluation. And the next evaluation, I'm going to get the same expression, 3I, but now I'm going to evaluate it with the value of 2. And notice that this is the same expression, it's just that it's been evaluated at 2. Since we're using sigma, I'm going to add it, the same expression, but now I'm going to add the expression when my evaluation has a value of 3. And we're going to do this until we evaluate it to the value of 5. So let's add the next same expression, but now it's being evaluated by 4. So I is equals to 4 now. This is my expression. And we're going to do the same one more time. 3I evaluated at 5, so that's 3, 5. And notice that we got to stop here because the top of my sigma is just saying you stop at 5. And that's what we did. We stop when we evaluate the expression at a value of 5. And now what we got to do now is just sum it up because we're using sigma. So let's just simplify this. So my first term is 3. My second term is 6. My third term is 9. My next term is 12. And my next term is 15. And we evaluate, and if we add them up, we got a value of 45. So what this is saying is that the sigma, or the sum of this expression, 3I, from 1 to 5, that's equivalent to just 45. Let's do one more example. Again, identify the variables that we're evaluating, which is k. Note that this is the whole expression that we're evaluating. We're going to start when k equals to 3, and we're going to end when k is equals to 6. So let's evaluate. Let's sum. So let's get the same expression, 1 plus. But now notice that what I'm going to do now is I'm going to evaluate k at 3 because I need to start at 3, not at 1, because that's my starting point. And notice that this expression is the same expression that we had in front of it, but now it's just being evaluated when k equals to 3. So now that we have the whole expression evaluated at 3, let's add the same expression, but now let's evaluate it when k is equals to 4 now. And again, notice that this is one expression. This is another expression. And we're going to do this until we go all the way to 6. So let's do this real quick. So my next evaluation, it's at 5. Notice that that's the whole expression. And lastly, we're going to do when k is equals to 6. So all we did, we just added the same expression, but now for every addition, we had a different value of k. And now that we have the actual expressions that we need to sum, let's simplify this. So 3 to the second, that's 9, plus 1, that is 10. My next term, 4 to the second, that's 16, plus 1, that's 17, plus 5 to the second, that's 25, plus 1, that's 26. 6 to the second, that's 36, plus 1, that's 37. And now if we add these expressions, or these values, we're just going to end up with the value of 90. So therefore, the sum of the expression 1 plus k squared from 3 to 6, that's equivalent to just 90. Again, perhaps I should have done this as well on the other example, because notice that I wanted to show you that it's just the same expression, it's just evaluated with different terms. So this is just a small refresher about what a sigma notation is. But how is this related to a series? Well, let's think about some of the properties for sums, because we're going to be using sum to define series. So let's think about some of the properties of this sums, or the sigma notations here. And let's do that by observing some examples as follows. Let's complete the following examples, and let's write down some observations that we can gather. Well, the first example that we're going to be looking at is when we perform a sum on a value. Notice that this doesn't have an expression. There is no, when it comes to the expression that we have in front of the sigma, there is no value to be substituting I with. So we're just literally just summing, or we're adding the value to as many times as is needed. So the way that this is going to look like is just 2. Well, if I substitute I to here, I just get a 2. Now, when I is 2, there's nothing to substitute, so I still get a 2 out. When I is 3, there's nothing to substitute, so I still get a 2 out. When I is 4, there's nothing to substitute, so I still get a 2 out. And when I'm actually stopped right there, because notice that we go from 1 to 4. So this is when I is 1, 2, 3, 4. And if we add those values, this is just to become 2, 4, 6, 8. And if we multiply 4 times 2, we get the same value. The observation here is that if we have a sum of just the constant, that's the same as just multiplying that constant how many times we add it up. So under a sum, if we're summing a constant, using sigma notation, which is what we did here, we were just adding the same constant using sigma notation. Well, that is equivalent to just multiplying how many times we added. So this is what we tried to show here. If we were just adding a constant, but that's the same as saying, well, in here, I need to add the same constant 4 times. Therefore, that's equivalent to just 4 times 2. Notice that we get the same value. So that is one of the properties for the sum using sigma notation. If we just add in a constant, that's the same as just multiplying that constant how many times we needed to add it. But now let's take a look at something that's a little bit more interesting now. Still, let's evaluate and let's see what observation can we observe here. So let's do the sum from the expression 2n from 1 to 6. So we're just going to do the following. So to the second, 2. I guess I'm going to keep it as red, just like I was doing on the previous examples. So this is for 1, 2, 3, 4, 5, 6. Okay. So let me just erase it and let's put it as red, just so we know what we're doing here. So this is 1, 2, 3, 4, 5, 6. Okay, so notice that is, again, what we're doing here, we're adding the same expression to n, but we're adding using a different evaluation. And let's see what we got here. Okay, so we got 2 plus 4 plus 6 plus 8 plus 10 plus 12. And that is equivalent to just 42. Okay, so let's put this aside. So what happens if we have a coefficient in front of the sum? Well, if we have a coefficient in front of the sum, we can think of this coefficient just multiplying the result that we got from the whole summation. You can think about it this way. When we have a coefficient in front of the sum, we can evaluate the sum, and then whatever result that is, we can just multiply it by 4. But notice that we already know what the sum is. The sum of the expression 2n from 1 to 6, that's what we found here. And we said that this is equivalent to 42. So therefore now this expression that we do have here, this is equivalent to just having 4 times 42, which is equivalent to 168. And to put it into words, what we can say is that a constant in front of a sum, which in this case, it is 4. So notice that this constant of 4, it's in front of the sum. What it does, it multiplies. Oops. What it does, it multiplies the sum by its value. So anytime that we have a coefficient in front of the sum, what we can do is we can identify the value of the sum separately, and whatever the result is, we can just multiply by what's in front of the sum. Another nice observation about it is that, and again, this is just an extension, this could have also worked out if, let's say, we have an expression. So let's say we have the coefficient in front of the expression here. This is just equivalent to just pulling out the coefficient as well. Just to give you a small example of this, let's assume that we have the expression 4 times 2 of n. So you have a coefficient multiplied by an expression. This is also equivalent to just pulling out the coefficient and leaving the expression intact. And now this, that would be the same result that we do have here. So this also applies if we have some kind of a coefficient in front of the expression. We can pull that coefficient to be in front of the multiplication of the sum, and now we just find the sum, and then we multiply by that coefficient. So these are two very big properties that we do have for the sums. And let's just do one more. Let's do one more property that we do have here for sums. Because now let's evaluate these 3 sums and let's see what we can gather. So for A, let's just evaluate this real quick. Let's evaluate the sum. And again, the expression is n plus 2, and we're going to add from 1 all the way to 5. So my first result is going to be 1 plus 2. My second result is going to be 2 plus 2. My third result is going to be 3 plus 2. My fourth result is going to be 4 plus 2. That's supposed to be a 2 there. And my next result is going to be 5 plus 2. And if we evaluate this, my first expression is going to be equivalent to 3. Then this is 4. Then this is 5. Then this is 6. And this is 7. And if we add all this is equivalent to 25. Okay, let's put this aside. Let's find the sum of this expression. Expression is 2n plus 1 from 1 to 5. So we're going to get 2 times 1 plus 1. This is my first expression. Then we're going to get 2 times 2 plus 1. This is my second. Third. I'm just going to continue down here. Fourth. And fifth. Let's evaluate this quick. So 2 times 1 is 2 plus 1, so that's 3. So that's 5. So that's 6, 1 is 7. That's 8, 1 and 9. That's 10, 1, 11. So our expression from here, it is equivalent to 35. Now let's put this aside. Now for this, let me just fast forward the video for this. Okay, so now that we're back, notice that this is the whole expression, but just when n is equals to 1. This is the whole expression that we do have here when n is 2, 3, 4, 5. And I guess for this one, you're just going to have to believe me. But if we add all this, it's equivalent to 25 plus 35, which is equivalent to 60. And again, you can verify this on your own time, but you will see that this is essentially what we got here. But now notice that I knew this result because I already know the property. And what the property that we're trying to show here is the following. Notice that when we find the sum of the first expression here, we got 25. When we find the sum of the second expression here, we got 35. So therefore, if we try to find the sum of an expression that it's made out of the addition of two small expressions, then what we can do, we can just evaluate it separately and then add up the results. So therefore, if you're adding, or if you're trying to find the sum, you're trying to find the sum of two sequences or two expressions, whichever, this is equivalent to just adding each of those individually and then add the sum properly. This is essentially what we did here. We said, look, I want to try to find the sum of two expressions. Well, that's equivalent of me finding the sum of the first, which we already found it to be 25. And that's equivalent of me to find the sum of the second, which is equivalent to 35. And now the sum of the whole thing is the sum of each of them independently. And this, you can verify this, but this, it also extends to subtraction. So therefore, this expression that we do have here, which is the sum of two expressions that are being subtracted, well, this is going to be equivalent to the sum of 4 of n plus 1 of n squared plus n minus the whole sum from n to the third plus 2n. And you can verify this as well, because also the summation, it extends to subtraction as well. So when we have a sum of two terms, when we have the sum of two sequences or two expressions, We're going to take a look at sequence in our next video. But at least when talk this, I'm sorry, not the sum, but the subtraction. When we have the difference or the subtraction of two expressions, well, this is equivalent to just finding the sum of the first and then subtract the sum of the second. And very important, and I guess gets overlooked a lot, in order for this property to be true, they both have to have the same starting point and the same ending point. So all we have done so far is just discuss some of the properties for sums. But our objective was series, so how are sums connected to series? So before we have the discussion, we have to introduce some vocabulary here, which is summarized in this box. It says, very important, when we sum the terms in an finite or infinite sequence, we call that sum a series. And that's what we're going to be taking a closer look on our next video. But today we're going to just talk about something more fundamental. But just recall here, when the sum of the terms of a finite or infinite sequence, we call that a series. So a series, it is the sum of sequences. Now, let's consider the infinite sequence, just for argument. So here we have an infinite sequence. And now, the sum of the first n terms of that sequence, it's called a finite series, or we also refer to it as the partial sum of a sequence. So if the expression that we're evaluating represents a sequence, if we add up to certain terms, which in this case we want to add up to the term n, then we can say that we have a partial sum of n terms. And we're going to take a look at one example in a second. And now, think about it for a second. So if we have a sequence who has infinite terms, and you want to add them all, well, that definitely must be some kind of an infinite series. And that will be this too, what we call the infinite series, and just the idea of series. Those two ideas we're going to go more into detail on our next lesson. But I do want to at least finish this lesson with a small example of what a partial sum is. So here we have a series. And now the reason why we can call it a series is because we can assume that the expression 3 over 10 to the I represents a sequence. And notice what we want to do. So for this series now, we want to find the third partial sum. So the notation for the third partial sum we're going to use S with the lower script 3. And now, let's think about this for a second. The expression 3 over 10i should represent a sequence where my first term is 3 over 10i, and my second term is 3 over 10 to the second, and my third term is 3 over 10 to the third, and my fourth term is 3 over 10 to the fourth, and so on. So what we want to do is, if we want to find the partial sum of the first three terms, what we can do is we can take a look at the sum and just add the first three terms in the sequence, where my first term, and again, we're all going to start at 1, at least in this example, and we're not going to go all the way to infinity, because if we want to find the third partial sum, we just got to add the first three outputs, where my first output is 10 to the first. Just like we said here, that will be the first term in the sequence, but we got to add the next one. That'll be 10 to the second. And then we're going to add the next one. And at this point, we stop, because we just want to find the third partial sum. We just want to add the first three terms in the sequence, because notice that this is an infinite sequence, because it just can go beyond. But If we want to add just the first three, that's what we refer to as the third partial sum. And at this point, all we got to do is just evaluate this. So we're going to get s to the third. So it shouldn't refer to as s to the third, it's just the sum of subscript 3. And if I add all this, this will be equivalent to 3 to the 10, 3, 100, 3, 1000. So if I add them up, this should be equivalent to 333 over 1000. So this is what we refer to as the third partial sum. Now, and this is going to be our conclusion. Another way of seeing it is, given an infinite sequence, an infinite series, if we want to find the third partial sum, all we're doing is we just find the sum from 1 to 3 of the expression 10i. This should have given us the same result. So I'm just going to do it a little bit fast here. And again, this is just equivalent to 333 1k. And again, on our next lesson, we're definitely going to go more into detail into the idea of an actual series and the idea of an infinite series. But for now, what we wanted to do is for us to have an understanding about the notation that we'll be using through our discussion for series, which is going to be a sigma notation. What we have done, we have reviewed what a sigma notation is. We have taken a look at some of the properties for sigma notation, and we have defined the idea of a partial sum, and we have done one small example of partial sum.